there. If you plug it into the formula up there, again, here we have A is 1, B is 0, and C is 16. So you will end up here of having a negative root, which means there's no imaginary numbers. Actually, under the imaginary numbers, the roots are 4i and negative 4i. But this is at this stage. So what does that mean? There is no solution here. That means there are no numbers to exclude from the real number. So the domain is all the real numbers. Okay? Because there are no points to exclude. Okay? Okay, so I see some confusion there. Any problems with understanding what we mean with domain and range? So basic concepts of functions, domain and you can think about it as input and output. Okay, input and output. Okay, students online, any questions regarding the domain and range? Okay, now something else here. As you see, this course is actually titled for the IE and ESE as Analytical Principles. Now here in general, you shall work systematically. So that means here in this case you will find out these roots here, which are -4 and 4, and they will split the real number line in areas. Let me just label them. This area here in between is area 2, and this area is area 3. So now you are interested in the sign of the amount under the root. So you can take test points there and this test point because it's premature, but I'm just advising you to assume that this is granted, that if whatever applied in one interval for one point will apply for the rest of the interval, because we have something that we call continuity. We will talk about it in the next semester. And continuity means you can take a test point, and whatever applies for test points, it will apply for the whole interval. Okay, so maybe I will, because this it's not about this particular question, we solved it already, but in general, so when you just a little bit more, okay, when you here we find the values that makes this 0. So here, if you like, I have, this is negative infinity, this is infinity. Okay, so I have 1, 2, 3 intervals. Okay, so interval 1 goes from negative infinity, of course, open here, up to -4. Interval 2 goes from -4 and 4, and interval 3 goes from 4 up to infinity. Okay, so now what we are going to see, that this systematic way of analyzing functions will be very helpful in the next maybe chapters and or beyond. In the second semester or advanced mathematics, you use it. What I am saying, we can take test points. Okay, let me just call them here test points in green. These test points, you just take test points, and remember our ultimate, let's say, our ultimate analysis here is to find out values that makes of x that makes this greater or equal to 0. Okay. Now imagine you don't know the approach we did before. You take test points. Now, of course, when you take test points, you take test points that are easy to evaluate, right? Easy to calculate. So here, of course, you can go and take to the left, for instance, 779, for instance, negative. And here you can take 955. And here you can take whatever, 3.4156, okay? But let's take this ones that make sense. So here I have definitely within this interval 0. So I take 0. Here I have, let's say 5. And here I have -5. Okay? So I take 3 test points. Let's say 0, 5, and -5. And now, because I have continuity here, it's ultimately this is a parabola, a polynomial. So I have continuity. Now, whatever applies for this test point will be valid for the interval where I picked up this test point. Okay? You can assume this is granted because you have continuity. Now, what does that mean, these test points? I plug in the values in the original formula. Now, if I plug in 0 here, I will be having 16 minus 0 squared greater or equal to 0. Okay. So in this region here, for this points, I get a number greater or equal to 0. So it will be for the whole interval valid. You got this approach? Okay. Now I go to the test point to the right, interval on the right from 4 to infinity. It's 5. So I plug it into here. So I will be having 16 minus 5 squared. So it will be -9. Is -9 greater or equal to 0? -9. Is it greater or equal to 0? No. Okay, so I exclude this. The same for -5. Notice -5, I need to square here -5. So it's again -9. And it is not valid because -9 is not greater or equal to 0. So I'm left up with the interval in between, which satisfies this inequality. So there are lots of ways to do it. You pick up the way you find, but this approach here is very helpful. Actually, you take the test points. Now sorry, you find the critical points. What does it mean? This is a critical point. So this one, critical point. What does it mean?
It intercepts the x-axis.
In this case, it means the to the right and to the left, it intercepts the x-axis. So maybe it was above, it will be below, or it means that something shifted there, right? Some behavior shifted there. In this case, from positive to negative, from negative to positive. Later we will see that this approach can be used for to find out where for instance the function is increasing or decreasing and so on. Okay. Now this is the first assignment. Any questions regarding the first assignment? All right, so and informatics. Who's studying informatics? Yesterday you had class, informatics class at the same time?
Informatics is today.
Really?
Yeah, 9:45.
But you're scheduled for mathematics for today then, right?
Sorry?
Your schedule for the mathematics class is Wednesday?
Yeah, only Wednesday.
Only Wednesday.
Yeah,
But what time you had the informatics class?
9:45 today.
Today?
Yeah.
Ah, okay, not yesterday, because here someone is writing. Ah, all right. No. Okay, because we had informatics online lecture too. Yes, please, go ahead.
One last question on the first question. How was it that you came up with R squared equals 16? Because if you.
No, no, I didn't come up. Yeah, maybe that's why you joined a bit later.
Yeah.
We said that to illustrate it better, we will take specific concrete values for R. Okay. Okay. So this 16 here, if you like, is just some special case,
So
special.
for instance, if I was to see that question, I wanted to give a solid number for R, I could say, oh, when R is 5, so 5 squared is 25.
Yeah,
Then
yeah,
say X
yeah,
squared
yeah.
would be
But in general, as the question is here, you will say that the domain here is negative R, and the range is 0 and R. So here, if you like, in this specific example that we solved, we just considered R equals to 4. Okay, it's just the general case will look like this here. Okay. Any other questions? Please ask if you have questions, especially in this session. Yes, please go ahead.
Yeah, if we have another function, for example, like the one you draw on the table, on the board.
Yeah.
How do we know? How can we calculate our range? How can we find it?
The range is from the graphic, you mean?
Yeah.
Yeah.
I know from the but if we don't have, we only have the term of the function. No, we only have the equation.
Yeah, yeah. Then it is okay. As you if you have a function here, then the domain will be x such that x and whatever in the domain. Yeah. Let's just write this as informal as the set that includes the domain. What is the range? The range is the value of y for all values of x.
Yes.
Okay. So here, if I call this let's say this set B, then the range is f of D as a set. Okay, so it's the number or the numbers that or the values that you get in plugging in all values of the domain in the function of R. So there is no, if you like, a patent recipe for that. Okay,
Yeah.
you need to think what this will result in if you plug in all values of
Yeah, but we can't plug in every value, so we look at characterizing points at the ends, the maximum.
Exactly.
Yeah.
You use the fact that we talk about continuity here, because
Okay.
then you take
Yes, later.
these reference points or this points. But and formally it is the range is the picture of the domain. Okay? Okay, so let's move to question number 2. Question number 2 is about the composition function. Everyone understands what's the composition function? This is a topic that is really very important, especially for those who's going to study mathematics for engineering next semester. We're going to have 2 topics in differentiation, what we call the chain rule, and in integration, the method of substitution of finding integrals, and they are closely related to this concept. So if you don't get this concept, you will be having trouble in understanding these let's say methods for integration or differentiation. So I will try to explain it here. Now, the composition function is, or the composite function is sometimes called, okay? is informally I would write it's a function of another function. Of course, there are some let's say assumptions that must be made. I will just write it in short. A function of another function. So this is exactly the meaning of the composition function. A function of another function. So the concept is I have a function that goes from a set, let's say, x to y, and another function that has, notice that y is a range here and it's the same time the domain there. Okay, so we just extensively talked about that yesterday. Okay, so this is the composition function. So you need to think about the composition function. It's creating a function of another function rather than a function of x. Okay, and now if composite G is a function that goes all the way from, let me think about it, is x up to z or z up to x. So here you would plug in f of g of x. So this is a function that goes from z to x. Okay. Now here the thing is that if composite g of x, how to evaluate it is just like plugging in f of g of x. So all you need to do is plug in this value here in the formula of f. So here, instead of evaluating f of x, you evaluate f of gx. Is that clear for solving this assignment? Is it clear? Okay. Now, if you have a specific number, actually here I would like to add something here, namely yesterday someone else, I think it was you, you asked regarding the domain of this. So let's try to find out if or G composite F or at 2. Okay, let's do the same for this function at the point 2 and see what happens. Okay, and part number 2, if we just add number 3 to it, I want to show you something that could be also the case in the case of composite function, that the domain, the point belongs to the domain of one function, but not the other. Okay. Okay, so start evaluating the composition function in part 1, if composite g of x. And notice that here evaluating, as you see in this formula, where is it? In, let me just write it here again. If composite g of x equals f of g of x, and g composite f of x is g of f of x. That means here, as you see, we are evaluating inside out in both cases. Okay, so that's why definitely this is not always commutative, meaning that if you just flip the order of the functions here, you will be getting a totally different value. Okay. Actually, you got only the same composite function if you have the function and its numbers. Anybody even got it? Yes.
So I believe I've written out f of g, and I know that I put gx in wherever I find an x value in f x, but for instance here, so I've obviously got 2x cubed plus would be 2x, but would I add those two together?
No, you know what you do? You just plug in 2x wherever you have x in the other one. So here this 2 originated from the formula.
Yeah.
There is another 2 because you are plugging here not x to x. Okay? But think about it. There is a common mistake that here when you plug in, of course here which one? I think F or G. This one. You are plugging in 2x, right? So here you have 2x all squared, not 2x, sorry, cube. 2x all cube. You got the difference? So you need to enclose it within parentheses, and then you need to calculate also 2 to the power 3. You got it? You got it? So shall I maybe write it here? So here you will be having f of g of x of 2x, right? And this is equal to 2x all cubed plus 2. This is from the original formula. And then for x, you just plug in, use parentheses, it will simplify things. And now in the denominator, I have 2x minus 2. So here, as you see, wherever I had x in the original formula, I'm plugging in g of x, which is 2x. But here, this is actually a common error that many students make. They just say this is 2x cubed. It's 2x all cubed. Okay? And if you break it down here, what you get? You get a to the power 3. Okay? Okay, guys online, are you following the composition function? Any questions? Questions? No questions. Okay. No questions. Great. So that means everything is clear. Did you add this third part, G composite F at 2? Yes. What was your answer there? Who's that? What was the answer? Sydney, if you can, sorry, I Kanji, I can't hear you. I saw you were saying something. You can write on the chat, please. So just, it's still working. Okay, just share your answer if you don't mind. Yeah. So anyhow, if you are done with this question, you can move to the next.
Problem solving, the next one.
You have problems in
Yeah.
which we can ask.
I wasn't prepared yesterday, but you know.
Okay. So you
Actually,
I will just write the things you need and tell me in which part you have the.
actually, we studied the vectors at high school, but it was different. Like we said, I mean, like part of physics. So, like, you know, finding like the degree between two vectors or, you know, a vector.
Yeah. This we had. Actually, we left it out yesterday because we didn't start the vector products yet.
Yeah. So,
But in general, I will tell you the formula, even though it's premature. But the thing is that you will be having. You can just erase this part here. You know the dot product?
That is like the square of A, B.
No, the dot product, not the square. The dot product is defined. So let me just make it simple and restrict it to three-dimensional vector. Okay. So assume you have a vector x1, y1, and z1. So on three-dimensional vectors. Okay. And you have another vector b, which is x2, y2, and z1. Okay. Then the dot product of u dot product u v is simply multiplying these numbers together, adding it to multiplying these two, adding it to multiplying these two. Okay. Dot product was here is equal to the sum of. Let me just make it big. So x1 times x2 plus y1 times y2 plus z1 times z2. Okay, so this notation means that you multiply component wise and you add them together. You multiply the x component with the other x1. Add it. So notice here that ultimately here you will be getting, multiplying two vectors, you will be getting a real number ultimately. So you're not going to get the vector. We will see another type of vector multiplication that will result in vector. But this one is a dot product. Now this value here, and obviously what is the magnitude of u, magnitude of v? Magnitude is always squaring the terms and taking the square of that, right? Same applies to v. Okay, so here you take the square plus. Here, be careful. I know that many students don't like these subscripts here and superscripts. So this one refers to the square. This one refers to just distinguishing the two vectors coordinates from each other. Okay, so this is one. Now, the dot product here is defined as u is equal to, I think it's cosine, right? Cosine theta, right? And one second. It's okay. It's cosine theta times the magnitude of u times magnitude of, right? Okay. Notice that the magnitudes here are numbers. This is a number, so ultimately you will be getting a number. So what you do to find where theta is also called the angle between the two vectors. So if you have two vectors here, this is u, this is v. So this is theta, and it's usually the inner. That's why it's called the inner product in many cases. Because you have obviously the intersection of these two vectors will cause two different, let's say, angles. Okay, this is one angle, this is one angle. We're talking about this angle in between. Okay, now if you solve it here for cosine theta, you will be having, of course, dividing the dot product by the magnitudes. Of course, to know the theta, then you get just cosine inverse of this amount here of u times v over the magnitude of u, magnitude of v. So this is the formula. Yeah. Cosine. So this is how we find that. But here you need to be very careful. I don't know whether you attended yesterday, but I told you whenever you use your calculator to work with trigonometry, just make sure whether your calculator is set to degrees or radian. because it makes a big difference. Okay, makes a big difference. If you set it to radian and you evaluate the cosine of pi, let's say, then it will consider pi equal the degree in degrees 180 degrees. However, if you set it to degrees, then it will evaluate the angle 3.14, whatever this constant is. And this is a huge difference. Okay, so just make sure what you prefer to work with. Even for the calculators online, you can just switch between radian and degrees. Okay, so does that help you?
Yeah, okay.
Okay, so in three-dimensional, for instance, what will be the first A dot B? 0 times 1 is 0 plus -4 plus 0. So it's -4. Okay. The dot product of A and B, 0 times 1 plus 2 times -4 plus 2 times 0. So you will be taking -4. Okay.
So we multiply it and we add it together.
Yes, one component wise you add it together. The magnitude 0 plus 4 plus 4. So here again you have to be careful because you are squaring -2 square. So you will be having 2 here, yeah? The square root of 4.
Yeah, can we have like a short review on the unit vector?
Unit vector is just dividing. Unit vector is when you construct the unit vector. Yesterday someone asked me a nice question. Why do we need the unit vector? Huh? Why do we need the unit vector? It's just like if you use a map, there is something, what they call it in maps, legend, I think, legend or no, not the legend, the scale, right? They will tell you scale 1 centimeter on the map will represent, I don't know, 5 centimeters there, whatever. So here sometimes you need to find out, I don't know how you learn trigonometry, but I remember that at school we used to work with something that we call the unit circle, yeah? Unit circle, so circle which has one as a radius to simplify things. Of course, teachers could use circle with 5 or 25 radius or 50 or whatever, but when you work with one unit, it's easy for calculations, right? Okay, so now the unit vector, so we use this notation. It's in German, it's called it's like nice vector, okay, it's YZ. Okay, now here obviously the magnitude of A or the norm is equal x squared plus y squared plus z squared all under the square root. Now the unit vector equals 1 over the magnitude of A times A. So this is the unit vector. And if you evaluate this, the norm or the magnitude of that one, you will be having magnitude of A reciprocal times magnitude of A, it will give you 1. So it will be having the magnitude of 1.
But what is the magnitude of the vector? It is like putting it inside.
Yes.
Oh, that's the okay.
Just squaring all terms.
Okay, that's the magnitude.
And you divide it, multiply it by the vector. Okay. And when you multiply a number by a vector, as I told you yesterday, for instance, here k times A equals, if this is A, then this will be A, sorry, k times x, y, z. So here you need to expand this concept. And very important, I don't know if you attended yesterday or not. Now whether I maybe it's a bit premature, but you all know matrices, right? Matrix is contains a rectangular arrangement of data columns and rows, or rows and columns. Now, a vector, it can be written as a column with one row, or it can be written as a row and one column. So whether you write 0, 2, -1 in this vertical format or in the horizontal format, it's the same, as long as you are interpreting this as this is the X component, this is the Y component, this is the Z component. Okay, so it makes no difference. So actually, students sometimes they ask me whether can I write this vector as 0, 2, -2 in one line. It's just the same. Yeah? It's just the same. Okay. So the rest we will be doing next week more with vectors, and also talking about vectors. Please. Turn the camera on the room. Okay. I will try. Camera control. And okay. Don't know which camera. Tell me what you can see now. Nothing. All right. Can you see the board?
Yes, sir.
What is the linear dependent and dependent?
Well, this we talked about yesterday, actually in some theoretical let's say context. Now linear dependency in algebra is the following concept. If you have 2 or 3 vectors, if you manage to write one as a linear combination of the others, then it is linear dependent. If you can't, then it's linear independent. A very simple, if you have, now someone was telling me yesterday, just correct that it means that you have 2 lines that are parallel, right? So this is actually the interpretation of the algebraic interpretation. But if you have it's dependent. So an example of linear dependent vectors, if you have the vectors u equals 2, 1, 3, and b equals to 3, sorry, 4, 2, and 6. Okay, and let's take another vector, which is 8, 4, and 12. Okay. Now you see here that I can write a vector. Actually, I can write v equals to 2u. Agree? So this is equal to 2 times 2, 1, 3. So if you just multiply here everything with 2, you will be getting 4, 2, and 6. Okay. So what does that mean? I managed to write v as a combination of the constant multiplied by the other. Okay. So u and v are linear dependent. The same applies for v and w. And now this concept here of the algebraic concept, it has different formulas. Now here, if you have a linear combination that is equal to 0, then it's not because of the vector, it's rather because all coefficients must be 0. So this is the abstract definition. Now, luckily in linear algebra, we will see very simple methods that will enable us to check whether two vectors are dependent or not. One of them is the triple product, multiplying cross product and then the dot product. And one that I personally prefer is I'm talking about three-dimensional vectors. You just put them in one determinant and so on. So that's why at this stage, I will urge you, please, just refresh your memories and determinants. So determinants, I don't know. So determinants, so you have here A, B, C, D, E, F. I'm talking in 3 by 3. So determinants are actually were introduced by Leibniz in the 16th or 15th century, and it determines it was called determinants because it determines for every square matrix number in R. And the concept of evaluating determinants is very important in linear algebra. So it will be important because we'll see that if this determinant of a coefficients of linear system is equal to 0, then this will mean it has no real solution. It's just like the square root of negative numbers. It will also help us in evaluating or deciding whether a matrix has an inverse or not. So evaluating determinants, I want just to advise you at this stage to maybe next week I will be giving you an introduction. There are a couple of very nice ways to evaluate determinants. Anyone work with determinants? School?
At school, we work with it.
Sorry?
We work with it at school. We work with the rows and the columns and how we can.
Yeah. So the Leibniz method actually in computation, I don't know whether you studied that yet, but in programming, there's a method that is called the recursive algorithm. Yeah. So recursive. Yeah. So always you start with some, let's say, value. Then you just increment it. So you remove one until you get to 0. I compare it to this. I don't know what's called in Russian. This Russian, Matochka or.
You mean the toy?
The toy where you have one toy embedded in the other, right? I think it's called Matochka or something. Anyway, yeah. Yeah, you have it at home. So if you want to get to the one inside, what do? You need to remove them one by one. And the typical example for this recursive algorithm that we use in computation is for evaluating the factorial, right? The factorial of a number, which is multiplying until you get to 1. And so very, very simple. You just say evaluating this, it means evaluating the one with negatives. So it will terminate, right? So if you want just this Matochka, if you have it at home, so if someone comes and he asks you or she how I get to if you have, I don't know, if you are just hiding some present in the core of this we call it figure or anyway, then you will tell him or her just take one, then after you take another one, and then you get to the kernel of this, and then you will stop, terminate. Okay. Now here Leibniz use this. So instead of just evaluating this what we call it 3 by 3 determinant. Very important. Determinants are only defined for square matrices. It do not make any sense to other matrices, okay? Square matrices means you have as many rows as you have columns. So Leibniz said, okay, you just hide the first row and first column. Then we will be left with a 2 by 2 matrix. Then we know how to evaluate the 2 by 2 matrix, and then we take it from there to evaluate this. If you have a 5 by 5, then remove one column, one row, you have 4 by 4. Remove one column, one row, you have 3 by 3. So it will stop at stage where you have a 2 by 2 matrix. Okay, but don't worry, we will get to this. And I will show you a very nice method. I don't know whether anyone knows this method, how to evaluate this determinant by just duplicating these two here. So you have here AB, DE, GH. I don't know how this works, but it works. Yeah. Then you have something like diagonals. So it's a little bit here, not very clear, but then you will be having you will be having diagonals that are falling this way and diagonals that are falling the other, and then you multiply them out and subtract. I like this method. It's very, very nice method to evaluate the 3 by 3 determinants. Remind me when we talk about it, I will demonstrate it for you. It's not very, very well known, actually. It's very, very widely used. I don't know why it works, but it works. Yeah, I don't know why it works, but it works. Remind me when we talk next week about determinants. And it is quite easy. Okay, so any questions regarding the so question number 3, actually at this stage, I just want you to, I will just tick the 3 these 3 parts and 5. Maybe at this stage you are capable of solving these 4 parts of the question that I already take. So important is adding, subtracting. It is done component-wise. Okay, adding and subtracting is done component-wise, meaning that if I want to add vectors A and B, I add the X to the X, Y to the Y, and the Z to the Z coordinates. Okay, component.
So it will be A plus B would be 1, 0, minus 2.
Minus 2, 1, 0, 1, 0, minus 2. If subtract, subtraction, by subtraction, you have to pay attention to the order because it's not commutative. If I want to multiply with a scalar or with constant, then I multiply it out again, component by component. Okay, will be expand to each of the coordinates. Okay, so for instance, here 3 here 5e. Let's do it. 5e, it will be 5 times 3, 15. 5 times 2, 10. 5 times 1, so 15, 10, and 5. Okay. And here regarding the magnitude, so you first evaluate the vector with, first evaluate the magnitude. Now notice here that the difference between 1 and 3 is that the output in number 1 is vectors, right? So you'll be having the vectors, 3-dimensional vectors, 3 values within parentheses. However, here you have a magnitude which is ultimately a positive or non-negative number. So here you will be getting the number. Here, to multiply it with a number, you will be getting the number. All right? Okay, number 4, the unit vectors, it's there, the formula. So what you need to do is to evaluate the magnitude of the vector, take the reciprocal, 1 over the magnitude, and multiply it by the vector. Okay, again, then you need to expand it component by component, and you will be getting a vector, and it's called unit vector. Since by construction here, how it's defined, it means it must be having the magnitude 1, because here, if you take the magnitude of all this one, it will be the magnitude of that one. So, but this is a constant, you take it out, then you evaluate this magnitude, which is the magnitude of A, then it will cancel out. So you see here, it uses the property that we talked about real numbers of the multiplicative index. Okay, you have the reciprocal multiplied by the number, you multiply it out, you get the unit, the neutral element under multiplication, which is 1. Okay, now here maybe this one here, let me just G composite F of 2. Actually, this is F composite G or G composite F composite G. Okay, if you want to evaluate it for 3, so let's simplify it here. So I have here 8x cubed plus 4x over 2x minus 2. Okay, now if you want to evaluate it at 3, you just plug in 3, straightforward. Okay, but if you want to evaluate it at 2, okay, so here you can take 2 as a common factor, right? So you have 4 minus 2, so 4x cubed divided by x minus 1. Is it 1 or 2 here? Yeah, it's 2 minus 1. It's minus 1. Anyway, so then you need to plug in here x. So here you will be having 8 times 2 to the power 3 plus 4 times 2. I'm just evaluating this here, and then you have here 4 minus 2. So this one, it will work. No problem. But if you want to evaluate G composite F, notice that here F is not defined at 2. So in this case, F composite G is defined, but G composite F is not defined. Okay? Now I saw some students, they just evaluated differently. They evaluate first the inner function for the specific constant and then plug it into the other, it will work. But here, since you evaluate at this stage here, you evaluate F composite G, then why reinvent the wheel? You just plug in 2 here and then you are done. You plug in 3, you are done. But you have to be careful. Like in this example, you will have G of F of 2, but F of 2 is not defined. So how will you proceed there? Then it will be, the answer will be undefined. Okay? Fine, yes? Questions?
I mean, that one is kind of wrong, right? F of 2x and doing that is kind of wrong. But
Why?
yeah, you're supposed to plug in like the whole of f into x, so that's supposed to be 2 multiplied by x cubed plus 2x over x minus 2 instead of that. Because that will be g of f.
You're talking about which line? This one?
The last, yeah. Like
The last one?
No, the mistake was in the upper line, yes. Because
This
it's
one?
2 times 4x potence 3, but it's 2 times 2 minus x. Because you took the factor before. If you look at it.
Okay, 2 Well, I will just say, if you expand this, what you will be doing? You multiply this with 2.
Yes.
Yeah, but I close this all in one parenthesis.
Yeah, but if you multiply 2 with our fraction, you don't multiply it in the denominator, right? That's the problem. The 2 in the denominator is missing. Like you didn't.
Yeah, so how will you do it then? You just take it for the denominator alone, denominator alone will cancel out, right?
That's right.
Yeah, so you have
Multiply it again, you will not like multiply.
Yeah,
with
you
the
won't
denominator.
get the thing you had before.
Yeah, you're right. So let's.
No.
Yeah, but if you take it in denominator and denominator, you take a 2 here, a 2 there, it will cancel out. So
You're right, like we did it, like in mathematics, we usually want to cancel some.
then it makes no sense.
Yeah.
Okay, so good that I plugged it in here in this.
Yeah, but
this thing. But then you can take 2 for the denominator, right? You can take 2 for the denominator, it's not a problem.
Like sometimes we want to cancel some number from a constant, we take the number from numerator and denominator and we just cancel them. So
Yeah.
we can like make it more simple.
Yeah, this is actually what this is strange. Come on. If you divide everything here by 2, is this not the case you are doing it?
yeah,
Yeah, you divide here by 2, here by 2. No, here. You divide by 2, by 2, by 2, by 2. Is this not allowed?
yeah, it's allowed.
Then you multiply here out. What is the factor?
2.
You divide by 2, or you multiply by 2.
Yeah, when you have to factor in front, you divide everything.
So you multiply with 1 half,
But not
1 half, right?
Yeah, the first one.
Okay, okay. Anyway, okay. As you see, sometimes simple arithmetic can cause problems. Okay, now, so let's leave it there and take a break, and then we will continue pure online. So for the students who didn't attend yesterday, we will continue online. You have the class here, right? With Sasha or Michelle? Okay, so let me. So see you next week.